Hello, welcome back to three-phase analysis. We're doing power calculations. This is kind of a neat problem that makes you think, and it also is another one of those problems that kind of forces you to use some of the new complex power equations that involve line voltage and line currents for three-phase circuits. So the problem goes like this. The complex power of each phase of a balanced load, each phase, the complex power is given by this, 384 plus J288 kVA, right? So don't forget that it's got a K here, so this is kilo, right? The line voltage at the load is 4160 volts. You're going to assume that's an RMS. You always do unless they tell you otherwise. Okay, so literally all we don't know if it's delta or Y load, but we know it's balanced, and we know that the power in each leg of the load, in each phase of the load, is given by this, and we know the voltage coming out of the load, the line-to-line voltage, I should say, the line-to-line voltage, is given by 4160. Let's look at part A first and focus on that. Find the magnitude of the line current feeding the load. So I'm not going to draw a picture here because sometimes the problems are simple enough conceptually where you don't have to draw like a single phase equivalent or anything. Besides, we don't know anything about the source at all. We don't really even know very much about the line. All we know is stuff about the load. It's all about the load end, and we know the power associated with the load. But in this case, we know the whole enchilada. We know the complex power S. P plus JQ. We know what that is for each leg of the load, and we know that the line voltage is given by this, and we're trying to find the line current. So you already know that you have some equations that calculate the power quantities in terms of line voltage, line current. So since we have the line voltage and we're trying to find the line current, it makes sense that you would go in that direction and look at those equations to back solve for the line current that we're trying to find. So then we go down here. All of this stuff is the summary that we've done. We can't really use any of these. We talked about why. We go down here and we see that no matter what the load is, we have these two equations. We used them in the last lesson. So it makes sense that you would want to try to do that. So if you know what the P is of a load, and you know the line voltage, and you know everything else in this equation, then you can calculate the line current. So the first thing you're going to try to do is go in here and use one of these equations. And in our problem statement, we're given, for each leg of the load, we're given P plus JQ. So you have P and Q. So you're thinking, oh man, I'm awesome here. I'm going to go in here and stick the power, which is the real part of that thing, in here. And I know what this is, and I know what this is, and you think, well, I know what this is. But then you realize you don't. You don't actually know what this angle here is, theta V minus theta I. You don't know what it is, so you can't just plug it in there, so you can't solve for this, and you're going to have the exact same problem here. You know what the reactive power is for each leg of the load, but you don't know anything. You don't know this angle, so you don't know the sine of it, so you can't solve for this. But then you realize that there's one more equation, an important one that I should have written down on this original summary here, that I didn't. It's not like anything's wrong or that I'm amending anything. It's just that there's one more equation. So I'm going to write it over here, and I just overlooked that when I wrote this little summary down on the board. But this is an equation that we've derived before. It's not a new equation. Okay, so here is, if you really just want to calculate the real power in terms of the line current and line voltage. Here's if you want to calculate the reactive power of the load in terms of line voltage and the line current. And then here's the equation if you want to calculate the whole thing at one time. So instead of P total, Q total, S total is what this one is. And it's going to look very similar. Square root of 3. Well, let's try to write legibly here. It'll be square root of 3 VLIL. Everything is the same as these other ones, but instead of a cosine or a sine, when you have this guy, you just make it into a phasor. You put an angle of your phasor here, and guess what this angle is going to be? It's going to be theta phi.